Welcome back to Introduction to Computational Fluid Dynamics. I'm Professor Steve Miller. Today we'll be talking about the classic solver algorithms which reside in many commercial CFD solvers. In the previous class, we discussed the idea of unsteady versus steady simulations. We then looked at time integration and implicit and explicit schemes. And we, of course, looked at the numerical methods that operate to create these types of solutions. Today we'll be talking a little bit more advanced solvers for particular types of incompressible and then compressible flows. In particular, we will be talking about the so-called incompressible flow algorithms, ACM, Simple, and PISO. And then we'll look at the predominantly used for compressible flow algorithms, PISO, which is a modification of the incompressible PISO algorithm, preconditioning techniques, and of course, FDV. Let's first look at the artificial compressibility method. This is basically used to solve incompressible flow fields, which of course comes from the name, which is a little bit misleading because of course it's compressible. These are basically pressure-based formulations, and they're used for incompressible flows to keep pressure fields from becoming oscillatory. What that means is that you'll see in a particular flow a checkerboard pattern in the pressure data from the solver when you look at the solution, which appears to be converged. So these checkerboard patterns appear for certain reasons, which you'll see in a few minutes. The ACM method is used to, of course, try to eliminate these checkerboard patterns in the pressure solution. This formulation is based on field variables, often involving the pressure, velocity, and temperature, where compressible flows will, of course, look at and examine densities, momentums, and energies. So the main difficulty in these incompressible solutions is, of course, the calculation of the pressure. And that's apparent in simpler methods where you find like an oscillatory pattern in the pressure, which is fictitious because of the numerical method. Let's return to our incompressible governing equations. We've written these in index or Einstein notation and in non-dimensional form. We have continuity for steady flows, momentum, and here are the variables with their non-dimensionalization. Say V infinity, L is a length scale, and of course, nu sub infinity is at ambient viscosity. Now, in the artificial compressibility method, the continuity equation will be modified to include artificial compressibility terms. These will vanish when steady state solutions are reached. For example, partial rho tilde, partial t tilde plus VII is 0. So you notice we've non-dimensionalized these equations. Here we write with a tilde as an artificial density. So this artificial density we want to drive to 0 for a particular incompressible flow. You notice that term is missing on the continuity operator. Nonetheless, we are trying to equate this term to the product of the artificial compressibility factor beta. So we've introduced a new factor beta in our equations of motion, which we call artificial, and it's just a coefficient which we set, and we try and drive this term. Of course, it's a small positive coefficient, but we try and drive these terms so that this equation is going to be true. So let's write out our equations in vector notation so it can be more compact, and we'll try and find an eigenvalue of it. In the first equation, we have, of course, our vector form with the definitions of W, A, D, and B. Here, W, A, W, B, W. This is all put in, of course, a vector form for pressure and velocity. So, for example, in W, we would have partial P, partial T, and partial Vj, partial T, right there. The coefficients of A and B are written down here along with their particular derivatives. So you've noticed that these coefficients are generally known in one particular space and time in the CFD solution. Let's, for an example, look at the eigenvalues of A right here. To find the eigenvalues, we would take, of course, the determinant of AI minus lambda I with the identity matrix, where lambda I are the eigenvalues for each particular order of the matrix. So if A is, of course, 4 by 4, we should have 4 eigenvalues. If we do the hard work, we can find that the eigenvalues are going to be u, and u plus the square root of u squared plus beta, and u minus the square root, and u minus the square root of u squared plus beta. This is very much like the eigenvalue analysis, which I talked about earlier in the class. Here, recall beta is now viewed as an artificial speed of sound or artificial compressibility. Of course, if beta goes to 0, then we return and find the original form for the incompressible equations, the original eigenvalues. This can be interpreted very physically in that you can view that the disturbances in the flow are traveling at a velocity u, and a velocity u plus u, and a velocity of u minus u. So you can see if u is near 0, or perhaps the mean flow velocity for compressible flow, then we'll have some eigenvalues which are very, very close to 0. This is a problem, and it might maintain or create a system which is rather stiff, and that is meaning it's slang in a sense, that it's hard to solve with a linear algebra technique or numerical technique in general. Nonetheless, by adding beta, you can see that we move the potential eigenvalues for some particular problems away from their 0 components. And this is excellent and a very wise thing to do because, of course, then the information will travel, the numerical data, through the solution out of the domain quicker. We would like to keep beta high enough such that the pressure waves will be allowed to travel enough to balance the viscous effects of the solutions, which are usually found, which we're going to show in this particular ACM method through the typical Craig-Nicholson method. Note that we showed in a slide in the previous lecture the Craig-Nicholson method. Now, by doing this, by having some positive coefficient beta, we'll now have a well-defined coefficient or set of equations. So the ACM method can be summarized by simply adding in some artificial speed of sound or compressibility factor to the incompressible equations in motion and simply solving them with a typical well-known technique like Craig-Nicholson. By doing this, we will have removed this so-called checkerboard pattern we can see in some solutions. You might come across this yourself one day in some commercial solvers, and you'll have to change the solver method, especially if you're in incompressible flow. Now, if we do not use this particular scheme of artificial compressibility, then two other most popular approaches are the so-called simple and PISO approaches. Neither of these are really simple to understand or implement, but their acronyms are just kind of a nice one because, of course, it turns out to be simple, but it's nothing but simple. So you might be wondering what simple stands for. It's an acronym, and it's called, which I'll call simple from now on, to just save time. It'll be the simple implicit method for pressure-linked equations. What a mouthful. This also can be used to try and eliminate the so-called oscillations of the solution, which we call with like a slang word of checkerboard patterns of velocity or pressures in each direction at every other node in the solution. So if you plot, say, a planar solution, you see a checkerboard pattern, it cannot be there. It's actually a numerical artifact. And if you look at the actual residual of the equations, you'll find out that the mass is actually not being conserved. This is a problem too. So you're not really finding a numerical solution to your equations of motion for incompressible flows. And you'll find that these particular difficulties can be bypassed through the use of so-called staggered grids within the algorithm known as simple. What that means is we might have a standard grid, which we create with our grid generation package, and then we're going to be using the solver to only look at it from an artificial sense as a staggered grid. For example, one set of the solver will look at points 1, 3, 5, 7, etc., and the other part of the solver will look at nodes 2, 4, 6, 8, etc. So one will look at even, and one will look at odd. And if you go up to the next row, then we stagger it by an increment of 1. We've already talked about the predictor-corrector procedure in the previous class. Here, we'll look at it again. Remember, the idea of a predictor-corrector procedure is that we make an initial prediction, which is like a mid-step, and then we correct it to the next time step or iteration of the solver. Here, we're going to do a predictor-corrector step with the so-called successive pressure corrector step. And of course, that's part of the name of the acronym. And we'll say that now we're going to decompose the pressure, which is the pressure we really care about, as an estimated pressure with a bar and a prime. These are not the so-called average pressures or fluctuating pressures, which we've already talked about and which we'll talk about later in turbulence modeling in the class. Likewise, we can do the same decomposition, that there's an estimated velocities and corrected velocities written with the bars and prime respectively. So we now have a type of decomposition. Nonetheless, we'll link this in with our particular solver into something like a predictor-corrector type method. In the simple method, the semi-implicit method for pressure-linked equations, we'll try and relate the pressure corrections to the velocity corrections by approximating the momentum equations. So now that we have this decomposition, we will approximate the momentum equations as you see here. Once again, you can see now we have a right-hand side of a correction and, correction, and the left-hand side will be the original left-hand side of the momentum equations with the nonlinear term. You can also solve this for u prime, like here on the right, with delta t terms. Now you'll notice something interesting. There's no viscous terms in here. That's, of course, because it's not part of this part of the approximation. We've dropped the nonlinear terms, the viscous terms. Now, we'll try and combine these particular sets of equations with the continuity equation. So we decompose the momentum equation with the corrector step, and now we're going to insert it and combine it with, of course, the continuity equation. This is the so-called, and what we find, the rather popular pressure correction Poisson equation, named after, of course, the mathematician, but he didn't find this equation. It just has a similar form to his, of course, famous PDE, which also carries his name. So now we'll have a correction of pressure with index II will go as the negative density over the delta t, the time step, times the change of the actual divergence of velocity minus the predicted divergence. And that'll be equal to this right-hand side upon simplification for I equals 1 to 2. This is a 2D example in formulation. It can easily be extended to 3D. Now we still have to enforce explicitly mass conservation at the current iteration before we go to the next time step, of course. That is to make the corrector step. So we solve these particular equations through the simple decomposition of the predictor equation method through the simple algorithm. Now let's look at the actual form of the simple algorithm. I've made a photocopy from a single part of Chung's book on CFD, which shows the method. And of course, he derives it in much greater detail than we have in this class. But let's go through the method together so that we can understand it, and keep the equations in mind of the simple method as we look at it. Step 1, or part A, we'll guess a pressure, P bar at each grid point. For the initial iteration, we could simply set it to an ambient value, or anything we want. It's like the initial condition. Then we'll solve the momentum equations to find V bar. That's the predictor step at the staggered grade I plus 1/2, I minus 1/2, J plus 1/2, and J minus 1/2. So here they're not going to every other grid point like we were showing or discussing earlier. We're actually going to half grid points or points in between. This is just like a midpoint or method which advances in time, but now we're doing the same operation to space. So you see, this is the motivation for the method. It's exactly equivalent. Then we'll solve the pressure correction. So we've made the prediction, now we make the pressure correction, which we showed, of course, for P prime on the previous page. And since the corner grid points will be avoided, because we can't perform this operation on the corners, then the scheme will be so-called semi-implicit and not fully implicit, as we previously shown. So it's a semi-implicit method. The correction of the pressure and the velocity will then be performed with the equations we've shown, and here they are, of course, again. We'll find the pressure at the new step as P, U, and V, based on, of course, the predicted values and, of course, the corrected values. So that's step D. A is shown here as a substitution. And notice the predictor step, of course, contains the viscous terms. That's very important. Now that we've gone to the next time level, we can simply replace the previous intermediate values of pressure and velocity with the new corrector values of P and V, and we return to step B. We then iterate from B to E over and over through every iteration. So for example, if we've done 1,000 iterations, iteration 1 will perform A through E, and iteration 2 through 1,000 will perform E through B, of course, and repeat. And then every iteration we can do a convergence check. This is a simple implementation of the 2D incompressible simple algorithm, which can of course easily be extended to 3 dimensions, and there's many papers written about this. So when you select the simple algorithm in the CFD code, which are usually commercially based to solve incompressible flows, this is the algorithm that's actually solving the equations we're looking at. Note this does not contain a turbulence model, and these equations can become much more complicated if, of course, we use this simple algorithm with a particular turbulence closure. So make sure that you understand that. Very important point. Let's look at some examples to illustrate graphically what's happening with the simple method. The correction of the pressure will actually accelerate convergence. If we use just a standard integration technique, then Integration, that is the number of iterations and computer wall time and power, will take much longer compared to a simple method. So we can actually modify the method slightly even more to find even better values. By, of course, introducing some parameter alpha. It's an empirical factor. So you see now the pressure will be decomposed into its predictor step and its corrector step, but the corrector step has an extra coefficient alpha. We just numerically experiment and find a value of 0.8, which seems to be optimal. We then have, of course, the same two other terms for nabla P and nabla P. Now, really, the previous discussion is for time-dependent flows where we have time-dependent terms. But this can become even more efficient if we use and assume that the flow is steady. So we might use the following finite volume discretization. And you might recall that we just talked about how we're looking at the grids which are staggered in 1/2 steps. And you might recall that we are looking at the particular values at half steps, for example, I of 1/2. So for the control volume view, we might have a cell-centered value where my cursor is, and we might go in the I 1/2 direction. So the control volume for U and, of course, P are actually staggered relative to the central control volume for P. This is, of course, part of the reason why they call it a semi-implicit method for pressure-linked equations. It's not explicit, it's not implicit, but it is semi-implicit in that it's a mixed scheme. For steady flows, the simple algorithm becomes even simpler, if you will, and we can substitute a conservation variable phi, and alpha will be called the under-relaxation parameter for subscripts P and NB. So these P and NBs will denote the node under consideration within the two-dimensional finite volume grid. Now, we can improve convergence even more through a simple little method. We can write A sub E minus sum of A and B of UE prime goes as AE of P prime P minus PE prime. Then E will be U sub E prime plus DE P prime P minus PE prime. This last point is simple is not that important in the big picture. What is important is the overall algorithm. You'll see there's certain advantages to this simple, but you'll also note that it's an iterative procedure, and it's semi-implicit. What if we want to try and improve the method a bit and look at a truly implicit method, which might, of course, have better stability characteristics for incompressible schemes? So another incompressible solver is called PISO, which is the pressure implicit with splitting of operations. You'll see and have noted that simple requires an iterative procedure. So it will obtain solutions, that is PISO, without iterative procedures and with very large time steps without much computational effort relative to the simple scheme and other schemes. This is why it's one very popular scheme to select in computational fluid dynamics. The conservation of mass will be designed to satisfy with the predictor-corrector steps, so it still, of course, uses the same predictor-corrector idea. The governing equations will now be a momentum equation and pressure correction equation. Let's look at them now. So we have a left-hand side, which is discretized, which is marches in time, with a velocity discretization between the next time step and the current one where we know the data. And the right-hand side will be, of course, the shear stress tensors and strain with the pressure term, say partial P partial X and partial P partial Y, at steps n+1. Now note, this is truly an implicit scheme as we discussed before, because of course we have time values of n+1. Remember, n is the current time level, and n+1 is the time level which we're trying to find. n-1 would be a time level in the past. There'll be a pressure correction associated with this. Let's look at this. The new pressure, which is discretized, will go as a negative rho over delta T of the differences in velocities minus this viscous term. So here, Sij, of course, is the derivatives of the sum of convection and viscous diffusion terms. We've lumped them all together as a right-hand side term. And we can calculate that usually because, of course, it's the previous and next time step. It's a closed form equation for, of course, the known and unknown field variables at n and n+1, respectively. Here we listed the rest of the equations. And we define Sij and, of course, the shear stress. Now, there's a predictor step And then there's two corrector steps. So the simple method had one predictor step and two corrector steps. This one simply has two. You can take a second to look at the form of equations and the current time levels. The first predictor step uses a time level denoted by star or asterisk, soup star, and the second one uses a double soup star. So through this simple predictor and corrector algorithm, we can implement the PISO method for the incompressible 2D system of equations. This seems like a lot of work, and there are certain characteristics of these schemes which are beneficial. For example, they're implicit, which takes a little more power to go from the next time step, but the time steps we can make are humongous and maintain stability. And we eliminate those so-called oscillations of the grid. So we can greatly increase the stability of the scheme by splitting Sij term, which we defined here. The nonlinear term and shear stress term, viscous term. And we'll split it into its diagonal and non-diagonal terms. For example, we would split Sij with I, that is the tensor Sij with derivatives I, as partial x of rho u phi minus k phi partial x, as an example. Now we can expand this term through simple discretization. So here's a continuum form. We can discretize it using, of course, our standard differencing, finite differencing techniques, which we talked about in our numerics class. And we can apply upwinding. So upwinding is going to take these parts of the stencil at midpoints and bias them towards the upwind direction. For example, if the current velocity is positive, we would use this so-called upwind direction, and if it's negative, we use this one. So look at the differences between the indices. The positive velocity, you use I and I minus 1, and the negative velocity, we use indexes I plus 1 and I. So this means the stencil is biased in the upwind direction. That uses more grid points, or nodes for the differencing approach and the direction of the wind. So using these operations, we can find the PISO with a splitting operation, which we just showed. And we'll arrive at these particular equations for rho u phi at I plus 1 and I minus 1, with, of course, an upwinding operator, which is equivalent to, of course, positive and negative velocities. Or if it's high speed, it might be a very, very small negative velocity and a very high speed positive velocity. So we can also rewrite Sij and these coefficients, alpha, beta, and gamma, and put them all in the scheme. Once we do all that, we can tridiagonalize the system for a structured grid, and you'll find a system like this, a tridiagonal dominant of beta, gamma, and alpha, beta, and gamma and alpha. This is the diagonal and off-diagonal term decomposition, which we talked about, of course, on the first line of slide 15. Now, that's an incompressible flow and the whole PISO algorithm, which you can, of course, implement when you run the PISO incompressible solver on, say, Fluent or Star or other commercial software codes. You can imagine it's a lot of work to implement these just for the laminar equations, but once again, they can also be implemented and applied to flows with a turbulence model. Now, what if we want to consider a flow which has compressibility, which is perhaps in a general sense seen as a flow with Mach number greater than 0.3? There's some modifications of the algorithm which we'd have to examine. We would have to split Sij once again to diagonal and diagonal parts as we discussed, and we can use the PISO algorithm applied to a compressible flow. We would once again have a predictor step and two correction steps. Between the correction steps, we would solve for P soup star minus Pn, which is known. Pn is known. This is the current time step in the known value, and insert it to obtain the new velocities v double soup star. Those values would, of course, be used to find and solve for rho. We can subtract these two particular equations and find this equation, which is labeled from Chung's book. We would look for v triple soup star, which, of course, in this case with I would be to enforce the conservation of mass. We would then find solutions which lead to this form, where vi triple soup star and p double soup star is v of n plus 1 and p n plus 1. So this would complete the splitting process, where v triple star and p double soup star will imply the exact solutions of v of n plus 1 and p n plus 1, which can be shown right here in these particular equations. For these particular procedures, you can see the full derivation and implementation in a paper by Asima, Gossman, and Watkins from 1986. This is the so-called PISO compressible form. Let's now examine the modification explicitly for compressible flows. We would add an additional corrector stage, which would be incorporated because, of course, now there's coupling between momentum, energy, and pressure. There's fluctuations of density and temperature with the effect of compressibility, which we did not have before, and they must be accounted for. So we can discretize the PISO scheme into particular time levels, like I've written down in the middle of the page. And we can summarize the new predictor corrector steps as now. We have a momentum predictor step, an energy predictor step, an intermediate momentum predictor step, and another momentum corrector step, a second one. Then we'll have an energy corrector, and finally a third momentum corrector. We can then and have to use the continuity equation based on, of course, the third corrector steps and the original density. And the pressure equation, which we can use to find a new pressure corrector step equation. These are all the equations that are used to find a 2- or 3-dimensional compressible flow of the Navier-Stokes equations with the pressure implicit splitting operation method. So take a second and just to review these equations. Because of time in the class, we don't have to review these. But if you're curious and you're running PISO methods, you'll have to know that these are what are programmed and validated with most commercial solvers. It's very rare today to find research-based solvers that use the PISO method. We've looked at incompressible flows and some workhorse schemes implemented in most commercial solvers to find the solutions. And we just looked at those equations and gave you a very broad overview of the algorithm to solve them. Now we'll look at preconditioning techniques. Now for very low speed flows, which are incompressible or creeping, or very high speed flows that are supersonic that contain regions that are very, very, very slow and locally incompressible, then the density-based formulations, which we showed, which are traditional, are very slow to converge. This is where the idea of preconditioning techniques came in. And you might have seen how we formed coefficient matrices in the previous methods of, say, for example, simple. We might be able to use preconditioning or linear algebra techniques on those matrices to change them from a very, very stiff system of equations to one which is less stiff, or one that can be handled by a numerical solver with much better ease. Why are very, very slow speed flows difficult and highly stiff to solve? Well, that's because the acoustic speeds are so much higher than the flow velocity, and the mean velocity might be very, very, very close to zero. And this means that some information is traveling very fast through the fluid domain, and some is traveling very, very, very slow. And so it would take a very long for the information to travel out of the domain and find, say, a steady solution for a flow which is very, very slow speed or very high speed with a very low speed region. So we'll try and examine the transition from spatially varying compressible to incompressible regions and vice versa. This will use the density-based formulation, and we'll use preconditioning matrices on the particular time-dependent terms. This will essentially and mathematically improve the convection eigenvalues for low Mach number or incompressible flow regimes. Let's take a look at these formulations now. As before, we'll rewrite our equations in vector form with Jacobians. So this is perhaps formed to a curvilinear or transform coordinate system using a finite difference approach. We have a vector u, which is our solution vector of p, the velocities and temperature. F and g, of course, are flux vectors. Here, we'll rewrite a as partial u, partial q, like we've done in the second equation. And q will then be this particular matrix. So we take the partial derivative of u with respect to q, and then we rewrite the first equation as the second with a equals partial u, partial q. Here we have a alpha sub p and beta sub t. These coefficients are defined at the lower part of the page. So it's a lot of work to do this type of decomposition and rewriting the equation in the form of the second equation on the page. Nonetheless, you can see it's now in a vector form, which we've shown for you. Now, let's try and look at the eigenvalues in the matrix, because the eigenvalues of this matrix will dictate the types of speeds that the information travels through the flow as we're finding a steady solution. So let's look at the eigenvalues of A through the same equation we did before. We'll take the inverse of A times B sub I minus lambda I. You can see here's A and B matrices in the coefficient equations. You'll see that in compressible limits, that is the density is going to some constant informally, we'll find that the eigenvalues become rather stiff, which is an algebraic set of equations which are L-conditioned, and acoustic speeds will become infinite. This means that as the Mach number of the flow becomes very small and goes to 0, and the density becomes a constant and that cannot fluctuate, that is, we're solving the incompressible set of equations, the speed of sound will go to infinity. This is rather troubling because, of course, it's an unphysical thing, but it's a property of making the incompressible assumptions, that the acoustic waves travel at infinity. This is not appropriate for finding an incompressible flow solution because, of course, in true incompressible flows, acoustic waves do not in reality travel at infinite speed. They travel at roughly the square root of gamma times r times T, the ratio of specific heats times the gas constant times static temperature. And so we want to modify these eigenvalues in some way, and so that we can make the system less stiff so we can find it. We'll do this through examination of the first column of the time Jacobian, which contains the derivative of the density with respect to pressure at some constant temperature. So if we look at partial rho partial p at t, it goes as gamma over the speed of sound squared. This is a well-known equation in compressible flow. It relates the changes of density with pressure at some temperature, and it'll go as gamma over the speed of sound squared. So this derivative will vanish for incompressible flows and the speed of sound will go to infinity. This is the core problem written down mathematically. To get around this problem, we're going to modify density essentially by multiplying it by beta. We'll have rho of beta sub t of partial rho partial p at some temperature, and expanding out the right-hand side, we can rewrite it as 1 over Vr, which is now our reference velocity, minus 1 over c sub p, which is the coefficient of specific heat at constant pressure times density times partial rho partial t at some constant pressure. You can see the mathematical operations here from thermodynamics to write out these equations and expansions. What might V sub r be through this introduction? We might simply set it for the speed of sound for compressible flows, or the square root of, say, the square of the velocity for incompressible flows, for perhaps boundary layers as an example. So basically, we do have to set it to some reference velocity. That shouldn't be too much of a problem, a single reference velocity for the flow. We can try and adjust the eigenvalues of the preconditioned system, and their adjustments will be done through, of course, the eigenvalue definition with A, and we'll write now that capital lambda goes the diagonal of u, y soup star plus the speed of sound minus u soup star minus the speed of sound soup star. We've now defined two new variables, y soup star and u soup star. Now capital lambda we'll introduce as the diagonal as, which are the eigenvalues of the system, as u, this y should be a u soup star plus the speed of sound soup star, a soup star, and u soup star minus u soup star. So the three eigenvalues are u, and u, and the last two are u plus the speed of sound and u minus the speed of sound. U soup star and the speed of sound soup star are now defined in this manner. These are found from, of course, the eigenvalue operations with the substitution of our modified speed of sound relation. You'll now find when the velocity is greater than the speed of sound that the eigenvalues will become u plus the speed of sound and u minus speed of sound. And if the reference velocity is approximately 0 or very, very small, then all the eigenvalues will be of the same order. So if a very, very small creeping flow, like here, if the overall velocity of the flow is, say, 0.01 meters per second, then all the eigenvalues will be modified to become of the same order of u. This is good. This means that our system is not very stiff and can be easily solved with a numerical method by simply applying this preconditioning technique. These preconditioning techniques were actually pioneered in linear algebra systems. If we just have a linear system of ax equals b, we can precondition the matrix A and B with the same multiplication and find a preconditioned system which modifies eigenvalues, and then we can solve the new system of equations, opposed to solving the original set, which might be impossible. This is exactly what we're doing with this CFD technique. We're modifying the eigenvalues through a modification of the speed of sound relation with a reference value introduction. We can further improve the efficiency in time-accurate solutions. We may try and utilize a dual time-stepping method, which we showed previously, of course, for a midpoint type method for simple and PISO. And we'll introduce a pseudo-time derivative. So for finding a steady flow, we will introduce a pseudo-time derivative, and we'll try and drive that to the 0 in a linearized iteration step form. So we can now take our vector equation, which was shown on slide 23, the second equation, which we discussed its formulation, and we'll find a right-hand side h, which of course will let be the incompressible form of the continuity equation. So the pseudo time step here, d tau, will approach infinity as the pseudo time step vanishes, and will recover, of course, the steady original governing equations. That is, this term will go away over time, and we have the same terms from the modified vector equation. That's really the transition from incompressible flow to compressible, and then looking at incompressible or compressible flows, of course, with a preconditioning technique. Let's turn our attention to a completely different concept for compressible flows that contain both high-speed flow and very low-speed flow. Flow field dependent variation was developed to handle high-speed supersonic flows and hypersonic flows where there's shockwave boundary layer interactions. In a shockwave boundary layer interaction in a very small region of the flow, we have compressible turbulence, we have flow which is creeping, like in the viscous part of the turbulent boundary layer near the wall where the flow is essentially zero, the velocities, and very, very high speed flow not far away from the wall where the Mach number might be 10 or 20. In this case, you might have flow at the wall which is about Mach number 0, and away from the wall it might be about Mach number 20. And so we can return to our generalized form of the conservation Navier-Stokes equations, which we've shown as a vector form in our fluid dynamics part of the class. We'll have partial u, partial t, plus partial f, partial x, plus partial g, partial x equals 0. So here you'll see something very simple. We can see, of course, a vector form of the equations, which we'll try and operate on. Now we'll expand in an explicit form for u of n plus 1, which would be the solution at the time step n plus 1, a form of the Taylor series upon this particular first set of equations. By expanding the first term in the Taylor series, you'll find what I've written on the bottom of the page at 27. We'll have u of n plus 1 will go as u of n plus delta t of partial u of n plus sa partial t plus delta t squared over 2 partial 2 u of n plus sb partial t over squared over 2 plus higher order terms. So you see I've done something a little bit strange here. I've kept the second order term, the first order term, and the zeroth order term, and I've thrown away the higher order terms. I've truncated them. And I've done the expansion about n and u of n plus 1 with delta t. Now the new time levels on the right-hand side, it's my choice to write them that way. I've essentially written something like an implicit method, as I'm operating at time level n plus sa, n plus sb. So instead of a well-defined sort of like midpoint method, I'm actually choosing two particular midpoints between n, time level n, and n plus 1. And I call these SA and SB. SA operates on the odd time derivative, and SB operates on the even time derivative. Let's see why we've made that choice. Here, now we can split and rewrite this first and second order time derivative terms on the right-hand side. The first one I've written as partial u of n plus sa over partial t goes as partial un of partial t plus sa of partial delta un plus 1 over partial t. And the ranges of sa must be bounded between 0 and 1. I can rewrite the second order equation here in the same methodology. Also, the coefficient SB is between 0 and 1. So I redefine these, and I can take these and insert and recover my, of course, Taylor expansion. Here I've written delta u of n plus 1 will go as u of n plus 1 minus un. So it's just a shorthand notation between the two time level solutions. And remember, these are vectors for rho, momentum, and energy. We can now substitute these equations in the previous one, and we will find u of n plus 1 goes as u to n plus delta t plus the SA term plus delta t squared over 2 plus the SB term. That's what this middle equation is. We want to do this through Jacobians, and of course we want to solve, perhaps in a finite difference approach, to a computational domain from the physical space, which has uniform spacing, of course. So we'll introduce the Jacobians. Once we do that, we can introduce them in terms of the convection, diffusion, and diffusion gradient terms and write the first and second derivatives of the constant variables in this form. This is simply our original equation with the right-hand side moved, the left-hand side moved to the right, and then we'll also find a second order term with our definitions above. We can combine these two particular derivatives and find this intermediate equation. We'll find partial 2u partial t squared goes as partial xi of ai plus bi times partial fj partial xj plus partial gj partial xj plus this mixed derivative. We can then substitute these terms into our form of u plus n of 1 equals un plus our higher order terms. And we'll find this large equation. It will be for delta of un plus 1 will go as delta t times all these terms which we previously substituted. But you'll see in this equation we have the typical flux terms on the right-hand side plus an SA times the partial derivative of the flux terms at n plus 1 plus the second delta t squared over 2 of the first order derivatives plus the second order time derivative terms, coefficient SB, with the flux terms, plus higher order terms. So these substitutions and changes, the variations with SB and SB, are simply resubstituted in the previous equation and solve for the time level n plus 1. That's a lot of work, and we've done this in a very careful way to find an implicit scheme, of course, for FDV. Why did we do this? And I'll try to explain this physically now. The parameters SA and SB will have certain physical analogies, and we'll find them and set them based on the current flow solution. So SB and SA are not constant coefficients. They will vary depending on the local flow properties. This is a kind of model, if you will. Now let's talk about SA first, which is of course operating on the first time derivative. If SA is associated with temporal changes of convection, it may be viewed from changes in Mach number between adjacent nodal points. We will set SA would imply that there's no changes in the convection fluctuations. Let's look at an example for the variation of SA for a shock tube problem. A shock tube problem, of course, is where we have a long pipe and we have a high pressure gas separated by a low pressure gas. A diaphragm separates them, and then an explosion occurs which blows apart the metal diaphragm, and the high pressure region is next to the low pressure region. This creates a shock wave which travels to the right in the system from high pressure to low pressure. Of course, the shock will eventually reach the end of the tube and it will reflect. Here we show particular solutions of the shock tube problem. We also show relative velocities, pressures, and temperatures. You can see in this particular case, SA will vary depending on the particular solution of where it is in the system. Let's look, instead of a shock problem, a boundary layer problem. For a boundary layer flow, SA would be one that is dependent on the fluctuations of diffusion, such as the boundary layer flows. Therefore, SA would be dependent on something like the changes of the Reynolds number or the Peclet number. A great working model for SA could be formed, and so FDV might actually have models that vary SA depending on, of course, the flux vectors F and G. It will be very beneficial to find general models for SA and SB. We've only showed you two particular models, SA for a shock tube problem and SB for, of course, a boundary layer problem. But this is rather cumbersome in that we have to create entire models just to vary SA and SB through the flow field. We'll try and seek out just general models. And how might we do that? Well, to provide these variation of these parameters and changes with convection and diffusion, we would need to know something about the current flow field. So we would need to make our models dependent on current flow field, which is kind of like this equation here at the top of the page. We note that SA and SB, to find accurate solutions for different kinds of flow fields, have certain physical properties. We might note that SA with delta F will be called S1. SA with delta G will be S3. SB with delta G will be S2, and SB with delta G will be S4. So now we divided SA and SB into 4 different parameters, depending on if it's operating on the fluxes F or G. So S1 we'll look at as first order convection FDV parameter. S3 will be the first order diffusion FDV parameter, and 2 and 4 will be the second order terms for the convection and diffusion parameters. Let's illustrate these particular breakdown of S1 through S4 for these parameters. The convection parameters we'll call S1 and S2, and parameters that are altered by diffusion physics and mechanisms we'll call S3 and S4. S1 and S2 are going to be more so dependent on Mach number, and S3 and S4 are going to be more so dependent on Reynolds number. And so we'll look at the first order parameters first. we can define simple models based on particular Mach numbers for S1 and S2. Here's one functional form for S1 and one functional form for S2. The first order FDV parameters can be shown on the right for S1 and S2 with y-axis for FDV parameters. S3 and S4 are diffusion-based. So for diffusion-based parameters, these simple models are chosen based on, say, minimum 0 or 1, depending on the Reynolds numbers. So you can see S1, S2 are depending on Mach numbers, and a very, very similar form is given for, say, S3 and S4, which are dependent on Reynolds number and the Peclet number. Let's look at one particular variation for a shock in a corner. Here, the flow moves from left to right. An initial inlet shock forms, and then in the corner, another oblique shock forms. So we have two oblique shocks, which are being turned, of course, by the flow. So the flow is pretty much uniform in before the shock, after the shock, and after the corner shock. And the corner shocks and the inlet shock have extremely large gradients. So we would expect S1 and S2 to be 0 in the regions between the shocks. At the shocks themselves, we would probably have very, very high values of S1 and S2. For the diffusion parameters, we would expect S3 and S4 to be 0, and we might have a rotational flow near the shock, where we would, of course, have S3 and S4 as 1. So by looking at this simple problem, we can estimate what the values are. And indeed, S1, S2, S3, and S4 are found as a matter of the solution as a function of space for steady solutions found through FDV. What S1 through S4 essentially do are parameters which scale and weight certain terms in the equations of motion if, say, the diffusion terms are dominant or the convection terms are dominant. And those go, of course, as the first and second order derivatives in the Taylor expansion of U, respectively. Let's summarize our full form of the FDV equations. And so if you have a research solver or a commercial solver and you select FDV for these very high speed flows, then these are the equations you'll be solving. The change in the vector U, which is the field variables, at time plus 1 plus delta t times S1 plus S3 minus delta t squared of the S2, S4 parameters plus delta t of the original fluxes minus delta t squared over 2 of the modified fluxes plus higher order terms will go to 0. So we have a single vector equation for the continuity, momentum, and energy equations with weighting factors S1 through S4, which are dependent on the flow field solution. You can always estimate S1 through S4 in advance as part of the initial condition, but it's honestly best to let them be calculated by the initial condition itself of densities, velocities, pressures, and temperatures. So you can see the physical phenomena in these flows are actually dictated by the FDV parameters themselves and inherent models. Now, what we haven't done is discretize this set of equations necessarily with, say, a finite difference method, a finite element method, or a finite volume method. So we would have to take this vector equation and discretize it with one of these three methods. Once we do that, we would also have to apply a turbulence model if we really care about modeling turbulence in high-speed flows, which we'll discuss later in the class. So this isn't the end of the story of FDV, it's only the beginning. And you can imagine how a researcher would have to take this equation, discretize it perhaps with a finite element method for high-order discretization, and then apply it and even modify these equations further to have additional equations in the vector form with a turbulence model. This could actually take years of someone's life, and even additional years to program it in a contemporary CFD solver. So it's impossible to learn and understand any of these methods, especially flow field dependent variation in a single class. You're probably feeling completely overwhelmed, and that's okay. It's just the tip of the iceberg of the field of CFD, which of course is perhaps seen as a mile wide, inch deep methodology and field. Let's take away some physical points of the FDV method. The first order FDV parameters, S1 and S3, will control all the high gradient flow phenomena such as shocks and turbulence. And so where we have high gradients of shock waves or very intense turbulence, S1 and S3 will dominate. These parameters will be calculated through changes of local Mach numbers and Reynolds numbers within each element of the flow field. They could be viewed as actual local elements of the flow. The contours of S1 and S3 will resemble the actual flow field features themselves. For example, in the shock problem, contour of S1 and S3 would very much go along these types of rotational flows. The fact that contours of S1 and S3 will resemble, say, Mach number density contours has been demonstrated in this previous example. The role in S1 and S3, of course, is to provide computational accuracy. The second order SDV parameters are a little bit different. They will provide exponentially proportional terms to the first order SVD parameters. However, their role is more to adequately provide computational stability and artificial viscosity. They were introduced, as you recall, through the Taylor series of expansion on the second order terms. If S1 is 0, these terms would represent convection terms. This implies that if S1 is approximately 0, then the convective convection is small. This might be a rather stationary type flow with a low velocity. The computational scheme will automatically be altered to take this effect into account when the governing equations are predominantly parabolic. That is, very low speed, or transonic. If S3 is approximately 0 in our solutions, it'll likely be a hyperbolic type system of equations, and the flow will be very, very high speed. The scheme will automatically switch to something like an Euler equations, where the equations are generally hyperbolic and or a very high speed hypersonic flow without many terms of turbulence or shocks, etc. If we look at our solution and S1 and S3 are not 0, and they're rather dominant, then we'll see that these indicates that the simulation is rather a mixed hyperbolic, parabolic, and elliptic in nature, which of course is like a Navier-Stokes system of equations, and the convection and diffusion terms will be balanced. So if S1, S2, and S3, S4 are not 0, and they're equal, we'll of course have a rather good balance between convection and diffusion terms. All these cases can actually be seen everywhere in a type of flow, and this will always be the case for incompressible flows at low speeds. You would not typically choose FDV for a purely incompressible flow. That would be a waste of computational resources, and you should look at something like the PISO scheme, or simple, or some simpler scheme, which we looked at in a previous class. Unique properties of the FDV scheme will be capable to control the pressure oscillations adequately without resorting to separately hyperbolic terms like the Poisson equation did with pressure corrections. That's one wonderful thing about the FDV scheme is we won't see pressure oscillations like we had in the other schemes. And you don't have to resort to some sort of like intermediate grid overlaps. Or, for example, like I plus 1/2 or I minus 1/2, as we saw in, for example, the simple scheme. Now, the FDV scheme could be applied to incompressible flows if we delicately balance S1 and S3. And of course, it happens automatically in, say, the near wall region of the turbulent boundary layer where this flow is high speed. If the flow is completely incompressible, that is the global Mach number is 0, but there's still flow fluctuations, then of course S1 will be 1. Then we'll set S1 equal to 1 explicitly, and we'll let the variation of the parameter S3 be determined through the flow solver. At the end of the day, all these flows, terms, and interactions between convection and diffusion will happen automatically if we use a general model for the 4 FDV parameters. In this class, we summarized some major algorithms for numerical solutions of incompressible and compressible flows. These are obviously a little bit beyond an introduction to CFD class and are often taught more so in depth in graduate CFD classes. Nonetheless, we have looked at some workhorse algorithms, so to speak, for many advanced commercial and industrial solvers. You will see ACM, simple, PISO, and variations like compressible PISO and maybe FDV in many of these types of solvers. Incompressible flows are certainly handled excellently by the ACM, simple, and PISO algorithm. If you have a compressibility in your flow, your solver should handle, of course, these fluctuations, for example, through the modification of PISO, preconditioning techniques for creeping flows, which are incompressible or compressible, and of course, the very famous FDV technique for very high-speed flows and hypersonics and high-speed supersonics. Now, there's many other algorithms. In fact, we could have a whole class just talking about all the different types of CFD algorithms. I was careful and just choose 3 or 4 of the most popular ones, which you'll see as choices in the solvers. From this class, try and take away the overall approach and realize what's happening in the solvers and why some of these choices are made. For example, to eliminate the so-called checkerboard problem of pressure in incompressible flows, or to handle seamlessly the different types of dominant terms of convection and diffusion in a high-speed turbulent boundary layer. Next time, we'll try and ground ourselves in stability analysis for simpler CFD schemes. The same stability analysis can be applied to these complicated schemes, but it's usually not performed and only examined numerically. Then we'll talk about residual and convergence and look at the so-called L1 and L2 norms. If we run these schemes, or schemes we previously talked about, then we will look at how convergence is achieved and how we measure error. We'll then formally define and look at convergence and give examples. Thank you very much for your time today. I'm Professor Steve Miller.